All right, let's get started. It's my pleasure to welcome everyone to Jayce Getz's talk on the Poisson summation conjecture. Jayce.
Yeah, thank you for the invitation. It's a pleasure to be here. This is the longest I've spent in Cambridge since undergrad, so it's been really nice. A little colder than I'm used to these days. So everything that I'm going to talk about today is joined with Pam Gu, Chun-Hsien Hsu, and Spencer Leslie. So don't forget to say that. And I want to start by giving a very rough version of the Poisson summation conjecture. And as Jans was pointing out to me right before this, I should probably put more assumptions in than I'm going to, but I'm going to try to streamline. And so here's the geometric setting. All right, so F is number theory. G is a reductive 3 over F. X, a normal geometrically integral scheme, finite type. So it's just a variety. And I give myself an action of G on X. Okay. So I mean, this is doubtless appeared somewhere else in the conference, but X is spherical if there exists an open Borel orbit with this action. Let me assume that assume for simplicity that X is affine. And I'm going to suppose some things that aren't quite necessary, but make the discussion simpler. Let's assume that I have a co-character into the center. Let's just say it's an isogeny for simplicity, or maybe just an surjective isogeny. So the center is just GM essentially, leading a character, and I'm going to assume that D following D check is multiple of the identity. I'll also assume that I have an automorphism iota from G to itself, such that iota following G check is D check inverse. So the example you should keep, well, let me go back. I'll say the example in a moment. So what you get out of this, you get the GM acts on X via D check going from GM to G, and I want to ask that this extends to GA. So what this allows us to do is it gives us sort of a notion of zero and a notion of infinity, right? So here's the maybe the simplest example maybe is that if I look at the action of GLD on some vector space V, I could just take D check of A, the A identity of V, and B is G, would be the determinant of G. All right, and this fits the bill for all these desiderata. It's a basic example. And so that's the geometric setting that I'm working in. What's the Poisson summation conjecture? Great. So again, I'm going to be a bit rough about this. I should also, I should put down names that are attached to this. Braverman-Kazhdan, World for Sakellaridis, And it's never appeared in print in the version that I'm going to talk about today. And there's, again, there should be maybe some additional assumptions that I'm not going to go into. I'm just trying to give a flavor. So what do we want? So first, if I pick a generic X in X, then I can look at the open orbit, which is G X mod G little x. So let's say I give myself far measures on GFE and BXFE for all V. So I get a measure on X circuit FV. All right, and I mean, if you want to make things simple, you might, in practice, it may not be possible to give an invariant measure on this space. We might want to look at that case. I mean, here's an example where we don't have an invariant measure. But let me sort of leave that. Be a bit vague about that. Okay, so here's the first part of the conjecture. There exists a Schwartz space, and it should contain attackly supported smooth functions on the open origin. It should be contained in SXFD, contained in smooth functions on smooth locus intersect L2 SXFD. Okay. And a Fourier transform fx S of XFB to itself, extending to L2. So implicit in this, I've given myself a measure on the open orbit. I'm just extending it by 0. And what should what property should the Schwartz space enjoy? So functions in S of X at V should be rapidly increasing at infinity. You should have a twisted equivariance property. So I gave you this involution earlier, which you could just think about as being inverse transpose in this case of GLD. And so I want the Fourier transform to take action of G to action via inverse transpose, essentially up to some scalar factor. And then if I choose a model of X over Cn inverse, then for almost all P, I ask for a basic function Vxp and S of X at D. It satisfies the following. I want to be non-zero. I want it to, I want the support of Vxp to be contained in the integral points. I'm writing ZP all of a sudden. I remember it. So I should say over and for a transform X of DXP is equal to B times P. I want functions in S and XV to be rapidly increasing with respect to any embedding that's into G into the map. Okay, so if I give myself some embedding into an affine space, I have a notion of zero and I have a notion of infinity. What else do I want? I want this S of X of V is local. So what does this mean? I.e., given some embedding into an affine space, want this to be closed under multiplication by the Schwartz space of X at the n restricted to the smooth locus of that V. Okay, so what this means is that if you give me any point on this, I can sort of localize my Schwartz spaces, my Schwartz functions around that point. Okay, so these are the local desiderata that we would want from the Schwartz space. Okay, given these local desiderata, you can define S of XAF to be the restricted direct product over B of S of X FD, and restricted direct product is defined with respect to these basic functions. And I should say B for these things. Hold over from previous talk.
Like the conjecture is open. Is
Yeah, so the conjecture so far is all this, but we haven't gotten to the meat yet.
Okay.
Right. So this is
So
the
now-
local.
now-
This is the local setup that
Right.
you want, and in many circumstances you can construct something. But the reason that I refer to it as the Poisson summation conjecture, first because there's too many names attached to it, and second because I mean really what we want is we want for this space this space of functions for Poisson summation to hold. So that's just the next point. So let's assume that F equals FV1, FV2, F away from V1 and V2 for some places V1 and V2. If this is an element of X. AF with support FV1 contained in X0 of FV. This is my open orbit and support FV2 contained in X0 FV2. Okay, so things are contained in the open orbit. The support is contained in the open orbit in both of these. And so the Poisson summation conjecture is that assuming dagger, the sum over all gamma in X of F of gamma is equal to the sum over gamma in the X of F X F gamma. So you have a Poisson summation formula. Okay.
So let's use a little older record quick.
So it's the support is actually in the open set, so this is laziness, right? So I could just have written it 0 and it would give me the same.
Well, maybe your other condition in the Fourier transform support.
Yes, you're right. Thank you. It's a bit silly to assume that. Thank you. It's silly to assume the same thing twice.
Yeah.
Okay. So here's an example. So returning to the basic example is that if X is equal to V and G is equal to GLV, then this recovers the Poisson summation formula. Assuming f of 0 equals fx f of 0 equals 0. And of course, this is an unnatural condition, right? And if we're working with, if we wanted to apply the Poisson summation formula to prove the functional equation of the Riemann zeta function, you wouldn't see the poles, right? So, I don't have a good, I have examples, but I don't have a good conjectural description for what the boundary terms of this. So let me say that for a general test function, this thing should be augmented by boundary terms on both sides. By boundary term, all I mean at this point is just whatever terms on the side give you, make it true for arbitrary functions. And when I have such a thing, let me refer to that as a full Poisson summation formula. So full Poisson summation formula. This is when it is valid for all test functions. Okay. And maybe so I don't forget about it. So the only case that I know of where there's sort of a really satisfactory example of a full Poisson summation formula is the case of the zero locus of a quadratic form. In the number of variables. And so in this case, what turns out to be, and I don't, this is sort of not the point of this lecture, but so this is due to myself and student Chun-Hsien Hsu worked out a lot of the local theory. And what's really fun is that what happens in that case is that you get the zero locus of the quadratic form. All of the boundary terms are given over all the zero locus of all the quadratic forms in the same width class.
Which group is that?
In that case, you can take the group to be just the orthogonal group of the quadratic form. Okay, so this has been submitted and it's up on the archive. On the archive for a long time. And the proof is fun because you use Arthur truncation and you look at all the extra terms that appear and you can interpret the extra terms that appear in terms of quadratic forms. Okay, so just to step back and talk about a few other known cases of this. So if G is simple and split, and P inside G is a parabolic, and we can consider the case XP, which is P derived G, the affine closure of this. So I take the derived group of the parabolic subgroup and plot out like this. So very early on, Braverman-Kazhdan proved a rough form of Poisson summation conjecture in this case. And what they really did was they constructed Fourier transforms at the level of the L2 space using normalized intertwining operators. And this is something that I sort of didn't discuss at the beginning of the talk, but sometimes the natural Poisson summation formula involves more than one space. So you may be moving from one space to another space. In this case, the natural thing is you take the space that you start with and take the opposite parabolic. And in fact, there's a whole family of Fourier transforms indexed by a certain Weil group. So this is all you get in the case where the parabolic is maximal. Maybe we could sort of stick to that case. The discussion. So they define this, and then they define the Schwartz space, I'll call it VK, of XP FV to be the Schwartz space of the open orbit. Plus the Schwartz space of the Fourier transform of which you get on the other side. So as an exercise, you can check that this is invariant under the Fourier transform, right? I mean, you just define it to be that way, right? So it's a very succinct definition, but it's sort of hard to get your hands on it. If you assume P is maximal, then my collaborators and I have done more work on this. So there's a construction theorem due to myself, Pam Gu, and another paper by myself and Sue and Leslie, which says there exists an explicit description of Schwartz space and explicit formula for Fourier transform. All right. So what do I mean by that? If you, I don't know whether or not I want to do that, but maybe I'll make a few comments about it. So these spaces, these XPs, I mean, let's say P is maximal, they have a natural Plucher embedding, right, in some vector space. And that vector space has a pairing. And you just integrate over the pairing, and that's essentially the Fourier transform. You have to renormalize, but so it really very much looks like a Fourier transform in the sense we traditionally think of. So I think that's quite pretty. Right, and this was all. I should also say this was also considered by Lay and Newell in a special case. There's another case that has sort of the same proof, which is due to myself and Pam Gu, and she's going to talk about it next week. So I'll leave that for next week. So it's the Poisson summation conjecture for Schubert varieties, generalized Schubert varieties, and this. I mean, she'll talk about it next week, I'm sure. But one motivation, I went and visited her for our sabbatical. It was one of the best decisions I made going to doing COVID in Korea, as opposed to the US. But anyway, so we worked on this because she was interested because she had these conjectures with Van Bach about these extra Poisson summation frame you get by restricting Eisenstein series to Schubert cells. So that was this. And then another result from a while ago, to myself and Pam Gu, which is different because it's not one of these spaces that's a horospherical space like this. If you let VI and QI be vector spaces with non-degenerate degenerate quadratic forms, QI, then you can consider the space V1, V2, V3 in V1, some V2, like some V3, such that Q1, V1 equals Q2, V2, equals 2, 3. So that's another example, and it's, as far as I know, the first example past the Fourier spherical case where we know this. She also mentioned my student Gu did an analog, let me just call it quadratic forms. Listed by automotive representations. GLN, this was her thesis. She's our student now. And Chun-Hsien Hsu, I say that we give an explicit description of the Schwartz space in this setting, but it's essentially something like you ask that the poles of your function are no worse than some L function as you go to 0, and the poles of the Fourier transform are no worse than some L function as you go to 0. But then you could, like, making that explicit is another matter, and Chun-Hsien was able to do that, and as a consequence, he proves that these spaces XP at V are local, and Braverman-Kazhdan definition is equal to our definition. It's quite nice because our definition is given in terms of the asymptotic, the germs of the Mellon transforms of our functions. It's sort of more analytically tractable, but this is much more succinct. And so the fact that they're the same is quite nice. All right. So now what I want to do is switch gears a bit and talk about, how we should expect to define the Schwartz space in some greater degree of generality. So let me just start with local considerations. So local considerations. Okay. So I'm going to explain the cheating way to define the local Schwartz spaces. So I'll sort of say what I mean by why this is cheating. But in any case, it is a definition. So let's assume that G is split. Let's even make the stronger assumption, which is actually quite important in applications, that the dual group of the spherical variety is the same as the dual group of the group. So, I mean, this is certainly a strong assumption, but this is actually true in many interesting cases. So conjectures of conjecture, let me say conjectures and work of Sakellaridis, Venkatech, and there's a nice paper in the Piatta case of Delarm, Ireland, and Sakellaridis. There's also related work that I don't want to get into in the real case, but what? With Volker? You don't have a poem paper with Hiram? Oh, it's with Herring? It's Delarm and Herring. Oh, okay. Sorry, Volker. Herring. This is the paper on Piatta, the Paley Wiener is with Herring. Okay. Apologies for that. I just get European names mixed up, I guess. Okay. So there's a Plancherel formula that lets you understand the Hara-Chandra Schwartz space of X circ. Okay. In terms of tempered representations on G of FB, some space of sections from the tempered representations of G of FB, and you can, to some spaces, maybe I'll just put a maybe in chats here. So this sort of technique actually goes back to Bernstein in this paper on Plancherel theorem. So I don't want to define these spaces, but the idea is that if I want, this is it's sort of Paley-Wiener, maybe I should write Paley-Wiener instead. It's a Paley-Wiener type theorem for the Hsien-Hsu space. So you can describe the Hsien-Hsu space of your space in terms of some set of well, measurable families over the space of tempered representations of your group. So just as an aside, this Hsien-Hsu space, it's designed to study L2 of X circ of phi, and to capture which representations are tempered. And okay, I want to, if I assume for simplicity that V is non-Archimedean, then TP, the tempered spectrum of GF, is a quotient, the union of quotients of R mod Z to the n. And so in the usual way, we have notions of rational functions. Rational sections. In the same way that we think of L functions as being rational functions, you can think about rational sections of this sheaf. All right, so under more assumptions on X, there should be the L factors and gamma factors L pi Rx and gamma I Rx attached to X such that the Schwartz space of X at V is, you take this Paley-Wiener map and you take the inverse of rational sections on CP GFE with holes no worse than phi goes to L phi Rx. All right, so I mean, Giannis was explaining to me before this talk that, I mean, you should put some assumptions on X. I don't want to try to, I probably will misstate what the assumption is so this is not the L function that is attached to X in the work of Sakellaridis and Venkatesh. It's sort of the square root of that. Okay, and so this is a definition of the Schwartz space, right?
So this is it's smaller than the space you evaluate or
Yes, so this Hsien-Hsu space is real. The functions that are not actually well behaved. They're just, it's like it's very close to L2. Okay. So I mean, and if you think in the case of like in the p-adic case, what is this space of sections? It's just sections that vanish off of some, I mean, each component of this will be compact. And this space is just sections that vanish off of a finite set of connected components. So there's tons of sections in this. It's very large. It's too big, and it does not have good growth conditions. But what I expect is that you should be able to define the Fourier transform on this space, because it's very close to L2, and then you just isolate this space that has, and the reason that you want exactly these rational sections, and this behavior is that it tells you exactly what growth properties you.
And is it obvious that this contains CC infinity, this definition of Schwartz?
CC infinity.
I mean, you wanted to, wasn't that one of your?
Yeah, I think
drawings?
this, yeah, I think it should be, yeah, because that would be the same thing as saying polynomial functions. Right, now it's a little bit more complicated in the Archimedean case, but I
But
mean,
in the group case, it's supposed to be the same as 60. Because in the group case, right? If X,
yeah, right, there's no, I mean, in that case, from this point of view, there's no L function.
oh, in that case, pi, there's no L function, so you.
No L function, the Schwartz
Really
space,
polynomial.
yeah, I really mean polynomials. Like the Schwartz space of GM. It's just compactly, on the non-Archimedean case, is just compactly supports with functions on GM. It's not the case for GA.
But you have to work with PW X inverse, so how hard is that to do?
PWX inverse.
I mean, that's your.
Oh, so I mean, this really is just a generalization of Mellon inversion,
So it sounds.
right? I mean, you can write down, well, okay, modulo whatever description you have of these components. A very nice reference for this is papers of Raphael Bouza-Plessis on. I mean, I found it very easy to read with his long book in Asterisk and then his work on God gross Prasad. He sort of goes through some of these special cases. It's very. There are many other references, but that was. Everybody has their own tastes, right? But I mean, I found those to be nice. It was easier for me to understand them. I mean, it's not as general as it could be, but. Okay, and then, and since. Okay, I mean, I should also maybe say that, of course, especially given one of the themes of this conference, there's geometric ways of thinking about Schwartz spaces, in particular the work of Giannis and Jonathan Wang on realizing the basic function as the trace of Frobenius on the IC sheaf. And Cho has advocated thinking about taking trace of Frobenius on all perverse sheaves that on the arc space of your spherical varieties, giving you the definition of the Schwartz space. But one thing that would be nice is if someone were to check that that's compatible with this, right? Because then that gives you a link between harmonic and L. And I think the experts know this, right? But I'm not sure that people have sort of explicitly stated that this is the expectation. Or maybe they have, and I just haven't read the paper, but it's not as well known as it should be that we actually sort of know what the Schwartz space should be.
There is a paper of Zukarnikov and
I haven't looked at it, so I don't know.
that's where you would see a suggestion about what the ramified part of that space is.
And from a geometric point of view?
Yeah.
I mean, even back in Vietnam, Cho, in the case of Monax, was saying that this is. Yeah, back in Vietnam, that sounds interesting.
Zukarnikov, Braverman. Sure.
So then what is the Fourier transform? Okay. So we have this keep on writing PL. So I guess I'm torn between Paley, Wiener, and Flasherell for the definition, but okay. So the Fourier transform should be the map that makes this diagram commute, where the bottom takes F and maps it to the section that is pi maps to gamma pi r pi F of X falling on M. So, I mean, I think it's an accessible problem to, and I'm right now with my collaborators, we're working on this in a very special case, but it's an accessible problem to make this precise. So it's an accessible. Make this precise. Maybe. Okay, but the complaint, which is legitimate, is that this is a bit circular. And in fact, I mean, I should also say that this is essentially the approach that Laurent Lafforgue in his work on constructing kernels for functoriality took. That he's, he has, I mean, maybe the setup is philosophically the same. You sort of know what functoriality should do on each representation, so you piece back the functions. It's a little bit less circular in the local setting because we have, I mean, at least for GLN, we have definitions of everything involved. So you get like a legitimate definition of whatever you have. But you would really sort of like to have a definition that doesn't involve L functions at the outset. I think some forthcoming work of Cho might do this in some special, Cho and Julian Wu might do this in some special case. Maybe he'll talk about it next week. Okay, so now let's pass to global considerations. So, global considerations. Okay, so the Poisson summation conjecture for X applies the functional equation and meromorphic continuation for L by R X, just by mimicking the Gaudemont-Jacquet argument. And in fact, for essentially any L by R Langland's L function, and construct X such that R equals Rx. And you can already just use reductive monoids to do this. Right? And then by the converse theorem, properties.
Before the new group of X, there was a new group of J, which is not satisfied for L1. Are you using this assumption?
No, I'm not. I mean, this is a philosophical point. Like, I'm not talking about the.
Yeah, actually, that assumption, how was that somehow you?
I mean, the only thing that I really used that for was that I didn't want to talk about what maybe I didn't use it at all.
Right.
Because I
see.
could just change the measure.
Not the whole, another one.
I mean, there'll be some smaller
Yeah,
pieces.
smaller, right.
Yeah, but I mean, that's not, yeah, it's just, I don't think. Okay, by the converse theorem properties of Langland's. I mean, everybody, I mean, this is sort of a well-known chain of thought, but I should say it. By the converse theorem properties of Langland's L functions imply much of Langland's functoriality. Which is, of course, the reason for people to start thinking about this in the first place. Okay, so we can reverse the logic to a certain extent. I mean, and I'll explain, it seems maybe stupid to do this, but let me explain why I don't think it's an entirely idiotic thing to do. So we can reverse the logic and say that if I know that L pi Rx is nice for all pi, I get the Poisson summation formula for X. So, I mean, it's sort of philosophically, this is the same argument as saying that the Poisson summation formula for Z sitting inside R is essentially equivalent to the Riemann, the functional equation. Zeta of x. So you do a contour shift and you can move back and forth. In general, it's not, I mean, there's sort of, it's not entirely obvious, I guess. Especially with boundary terms. For arbitrary testing. All right, but again, this is a bit circular, right? Because, well, the reason that we are studying the conjecture is that we want to understand properties of L functions. So if you use properties of L functions to prove cases of this Poisson summation conjecture, I mean, it's sort of not what we want to be doing. So approach is again circular. Somehow this circularity is worse than the previous circularity because, you know, for me, I want to understand the analytic properties of automorphic representations. So I'm willing to, I mean, if I have to do something circular locally, fine, right? But, you know, I don't want to be assuming what I want to prove. So then the next thing I want to talk about is 2 strategies to break circularity. Right, and the first is is something that basically maybe lies at the genesis of the Rankin-Selberg method in theory of spherical varieties, and that's the idea of restriction. Okay, so sometimes let's suppose that x cross g to x is spherical with large stabilizer. So the thing that you should think about is the case of G mod P. Then the generic stabilizer is this big old parabolic subgroup. So e.g. x3. So this has a very simple spectral decomposition because the stabilizer is quite large. So it has a comparatively simple spectral decomposition. Okay, so sometimes H inside G still has open Borel orbit. So this tells us that the spectral okay, person down. Okay, so spectral decomposition of L2x AF with respect to the H action may be richer. So here's, I mean, and examples of this, of using this technique in the literature abound. So here's just 2 of them. I mean, the map from SL2 cubed to SB6 is a nice example, and this gives you the triple product L function. Also the doubling technique. This technique has been around for a long time, has been exploited by many. Right? So the second technique is something that I don't think has been exploited, I mean, to the extent that it could be. So this is what I call the fiber bundle method. So I'm going to
understand what you're saying about. So what are you proposing?
So in the,
Stabilizer lead to it.
well, what I'm saying is that if you have some representation that is somehow, I mean, if the spectral decomposition of X as a spherical variety under G is simple, then we sort of understand how to prove Poisson summation formula for it, like in the theory of Eisenstein series.
Right. We have cases beyond the theory of Eisenstein.
No. But I mean, but I'm just saying that the idea is, right, if you have some space on which you know the Poisson summation conjecture, you could try to restrict,
To a smaller cell. Yeah.
right? And this is not like my idea, right? I'm just pointing out that this is an idea.
But in this example, a trivial product, what is the stabilizer?
So you take this acting on SP6 mod the Siegel parabolic,
The SL2 is 3.
and the SL23 maps into this by A, G, A1, A2, B2, A3, B3, with respect to a particular form. We're sitting, this is the triple product, right? So you take SL2 cubed sitting inside SP6. I think I wrote it down with respect to this form. Right.
Yeah.
And then you so you have this acting on the space of the Siegel parabolic, which is where you have the 3x3. 3x3, that stuff up here. And then if you restrict to this, the stabilizer of the generic element is the n equals 3 case of Janus's favorite.
Yeah, it's 0 uniform.
Right, yeah.
Okay.
Other questions on?
I see, so that's the way kind of forming the triple product. Has a
Yeah. And this is just, this is sort of the genesis at some level of Rankin-Selberg and spherical, characterizing what sort of situation you can. Okay, so then the second technique is the fiber bundle method. So what is this? So let's say I have a diagram like this, and these, I didn't know what to call these things because they're not Borels, they're just base schemes. Okay. So apologies, I mean, maybe I should call them something different, but I give myself a diagram of G equivariant maps. All right, and I'm going to assume for all di and bi of f that if I look at the fiber and take its closure, which is P I inverse B I, just the affine closure of this is spherical variety for G L. Right? Then Poisson summation conjecture for each BI implies the same for X, at least in principle. Okay. I mean, you can just take, I mean, you do Poisson summation along the fibers here, and you do the Poisson summation along the fibers here, and I mean, in fact, in many circumstances, you want to do a Fourier transform with respect to these, maybe in some order. So let me give you a really nice example. This is the thing that made me think about this idea. This is maybe David Kazhdan pointed this out to me. And this is again, I mean, it goes back to Alphonse Graves. But the example is that you look at SL3 mod the maximal unipotent. So when you take the closure, this is sometimes known as basic affine space. So I want to realize this is the set of B check in GA cubed cross GA cubed dual such that D check would be equal to 0. Okay, so it's just a cone. And so this has two projections. It has a projection down to GA cubed minus 0, projection down to GA cubed 0. Yes. Check. So I can just map it to the first vector and the second vector. And the fibers are GA squared, and they carry a symplectic form. So what happens here is, this actually goes back to an example that I gave near the beginning of this talk, that if you have, if you have one of these G mod the derived group of a parabolic, you have sort of a Weil group worth of Fourier transforms. So these are the Fourier transforms that are attached to two simple roots. And then when you take, it's interesting, for example, that if you take an appropriate combination, you get the long Weil element, which has nice equivariance properties under O3, whereas each of these individually do not. I think take O3 defined with respect to this. So my point in saying that is that sometimes, even though the individual Fourier transforms may not have the equivariance properties you want, some combination of them does. Okay. And this technique, I do not think has been exploited to its full potential. That's maybe the most important point of this talk. Okay, so now I want to talk about the setting that I want to briefly outline the setting that we're working on to apply this technique to try to study triple product functions. Okay, and it's a bit technical, but I want to try to at least give some indication. Maybe I'll say strategy application. Product functions. All right. So let me start by writing down an example of this that first, well, okay, let me start with just one factor. So let me take R bigger than or equal to 3. I'm going to define a space of matrices. And R is a, so it's R binds 2, 2 matrices where U1 wedge U2 is equal to 0. I'll let N be the nilpotent subgroup or unipotent subgroup of GLR, with N equals I combines 2, 2. And I want to construct the following. Sakellaridis and Venkatesh call these Whittaker inductions. So here's the space I'm looking at. I want to look at GA cross GLR M wedge over M wedge, M cross wedge, GA GLR cross M wedge. And so the map sends B, M, minus 2, Z, 2, M, to B plus M, B minus 2, so this GA is recording an action that, when you turn this into a space of Schwartz functions, it's recording the action of some additive character. And the point here is that action of the additive character depends on the base space. All right. So then I want to consider VR, which is the quotient. And think about it however you want. I mean, maybe it's best to think about it as a stack, but you can also, I mean, not really going to need that so much. So this is a GA torsor over GLR mod M cross M wedge, right? So this is the basic object that I want to study. Now I want a triplet. I want to triple everything. So R underline is R1, R2, R3. GLR underline is GLR1, GLR2, plus GLR3. And M wedge is M wedge R1, M wedge R2, M wedge R3. I didn't put an R3 into the notation there, but this is the R. So for X in SL2 cubed, write X equals A of X, B of X, C of X, D of X. And then let Y tilde be U1, U2, X, and M wedge SL2 cubed such that U1 C X plus U2 X 0. SL2 cubed acts on these three, which is GA squared tensor squared tensor GA squared with open orbit. So I get a map Y tilde to M wedge cross V3. Okay. And this map is doing is it's just it just records the CX and DX, each of these variables, and takes the tensor product. And I'm going to let Y be the image of Y tilde. I apologize that this is, it is what it is. I don't know how to make it any less thick. Okay. So then what? Y admits an action of GL R minus 2 cross SO2 cubed plus GA GM. Okay, the SL2 cube acts on this tensor product. The GLR minus 2 acts on this U1 and U2 here, and the GM acts via scaling on V3.
What is you have a triple R, right?
Yes. Ah, right.
Oh, it's
Yeah, so it's
three
thank you.
groups.
Yeah, so 3 groups. Chalk here today. Okay. All right, so then the space that I want to study, the thing that I'm going to apply this fiber bundle method to is VR cross over M wedge Y equipped with GLR minus 2 plus GLR underline plus GM plus SL2 cubed. All right, So what's the fiber bundle structure? Well, it's written right here. Fiber bundle structure is the following. Let me call this P1 and P2. And let me talk a little bit about what the structure of these two things are. So the nice thing about this is that the fibers, if you work this out, they are vector spaces. And this is the reason for this funny definition here. So this is very similar to what you do in the triple product for GL2 cross GL2 cross GL2, but there you have the symplectic space. So the observation is that you can set things up. So you take essentially a quotient of that, and it's a quotient of a sub, but you get a vector bundle. Right? So what's this? So the fibers of this, V sub I, V sub 3, it's just 3 copies of, V sub R underlined. And it's not, it is a Whittaker induction over, so it's a Whittaker induction over this, it's a VA bundle over GLR mod N cross N wedge.
N was,
So N, this
the
this is the unipotent subgroup of this function. So you're going to have a left action of GLR minus 2 on this, right? And it also acts on this base space.
but then when you fiber product over N, it's like the Mn factor disappears, right?
N factor disappears.
So if you take the fiber product of VR over Mn with Y tilde,
Yeah.
this is the same as saying fiber product of there is no Mn, like expectation.
Well, Y also has it.
Right. So you can keep the Mn from Y and then take actual product with GLR mod N, right?
Well, okay, this is the space, this is the base space. This is not VR. VR is a GA bundle over this.
Yeah, okay.
Right. So I need I need a Whittaker thing. Yeah, I need to have
And this has an action of what?
this has an action of GLR cross GLR minus 2. And yeah, that's what I'm using on this one.
Where does the action of GLR minus 2?
It comes from acting on the left because I have this.
But have some Whittaker character that's not preserved.
Right, it also acts on this.
No, I mean the action. When it acts on the left, it doesn't preserve the Whittaker character, right?
Right, but you have it act on this term as well.
Then you don't need it to preserve the character.
Well, it doesn't preserve the character, it moves the character.
It moves the character.
Right. Right. I mean, so what you can also think of this, there's another way to view this as you sort of, you can think about it as a Whittaker induction for a GLR minus 2 and an SL2 down here. But I want to take that SL2 action and I want to modify it so that this factor sees the triple product L function. Right, and I'm sorry, I don't know how to make this any less technical, but I mean, okay. But the observation then is that if I look at these fibers, the fibers are vector spaces. And these fibers, I mean, they're Whittaker inductions. With associated L function, L of pi cross, well, L of 1/2 pi cross pi prime. This is on GLR underline, this is on GL minus 2, and L of 1/2 pi dual and some character. Right? And so these are not triple products, these are just products of, normal things that we understand. So from what I said earlier in the talk, since we know the L functions, we should be able to construct right? So the idea, and there's many things that could fail, right? But the idea is very similar to what we do in the context of the trace formula. You want to prove some trace identity. You don't know how to do it directly, so you reduce it to situations where you can prove the trace identity that you want spectrally. So you sort of move back and forth between the geometric thing. Well, first you want to do something spectrally, move it to geometric, then you move it to a simpler spectral situation. You move back, play this back and forth game all the time, right? And so the idea is to try to do that in the context of the Poisson summation conjecture.
I don't understand what it means that the fibers are vector space, because the fibers of the map on the left are the same as the fibers of y tilde over m n.
Right.
And they don't look like vector space. Like if you fix u1.
No, so there's a quotient. I mean, because you take this, you take this map, and you're right that if you look just at this, it's not vector spaces.
Oh, I mean, there's a Cartesian square, right? This map on the left is base changed from the map y tilde maps to mn.
When taking y tilde and mapping it, I mean, it's not base change from that. I'm taking the image of this in here. It's killing information.
No, but V3 doesn't appear there, so I'm just saying.
V3 does not appear here.
I'm just saying that this is base change from the map y tilde mapping to mn.
Y to the what?
Y tilde
Yes.
goes to m sub n.
There's no, oh, is this the issue? There's no tilde here.
Oh, there's no tilde there.
Oh, okay,
Oh.
okay, so yes, it's not, sorry, it's a straight mark.
Oh, okay.
Oh, so why?
The only reason for doing the reason for replacing, so you get a fairly nice space if you look at this, it's cut out of, if you look at this space, it'll be cut out of M wedge cross SP6 mod, the Siegel parabolic that I looked at before. Right, but if you go to this quotient, then it kills, it's a finite to one map that brings you down to something that's generically a vector model.
But is this portion just taking a matrix in SL2 and
So you take this-
mapping it to C, comma D?
Yes,
Okay.
only you do it in each factor.
Okay, good.
Yeah.
Okay,
So
okay,
then-
then I'm
yeah,
fine with
yeah.
the vector space.
Yeah, so I mean, and that took a long time to, that you could do this. Because of course, if you work in this, then it's not so clear what, how we should work with the, oh, we're out of time. Okay, so that's great, because that's all I wanted to say. So, thank you.
So are there any questions? And I also invite the 10 people who are online with us to ask any questions by putting them in chat or just saying them out loud. Any questions?
Can you repeat the statement that you made about the relation of this diagram to the dual function?
So the statement is that if you take this and you integrate it against, you do the standard, I mean, you have a spherical variety, you have an action of a group, and then you take a couple cusp forms, you integrate it against it, and the statement is that you get something that is the triple product L function.
Okay, but because I don't see a spherical variety or.
Right, so this is the variety.
The product, I mean, the product.
The product.
And the action-
For the action is a
It's
spherical variety.
it's the action of GLR cross GLR minus 2 cross, so I'll put it as, SL2. So really, okay, it's some form of this. Let me not be specific because of this finite to one map. You have to play with this. Let's just say that Lie algebra is this. Okay. So I take a cusp form here, a cusp form here, and on this I just want a character. Take these three automorphic this automorphic information and integrate it against functions on that space.
But what is the expected L function?
The expected L function is, so this thing lands inside I1 tensor pi2 tensor pi3. This is inside pi1 prime, right? So the expected L function is L 1/2 pi1. I mean, there might be a dual that's missing. I think I maybe have to put it in here. Posted by Ada. And then there's another factor that involves some Rankin-Selberg thing.
Over the pi prime.
Yeah, so the other this is the meat. And then the other factors are products of L functions we already understand. That are essentially coming from these fibers. And what's the justification for that? You can just take integral points of this thing and then integrate it out. And then you just unfold. It unfolds to a Whittaker model and you compute. And it doesn't give you the L function on the nose because we don't have the right Schwartz space yet because that's what we're building.
There is no action of CL R-2.
So
Because you have descended to the space Y.
Y also has an action of DL2.
So maybe we should hold off on the questions till our formal recording is over. And I do want to again ask if anybody who's online would like to submit a question. And if not, then I think we should end our formal presentation here. We can continue conversation. There's actually refreshments upstairs. And so let's thank Jayce again. Thank you very much. I'm going to stop the recording. Thanks for coming, everybody. Take care.